Hello, everyone. My name is Simon Pierce, and I've come here today to talk about global server load balancing in Kubernetes. Glad you all came to the talk today, and hope you're enjoying DevOpsCon. It's freezing cold in here for some reason. Someone overdid it a bit with the air conditioning. I'm feeling a bit cold, but otherwise everything's good. Um, if you find any mistakes with my slides, I didn't have very much time to prepare this because I didn't know until yesterday that I was supposed to be holding this talk today I had to jump in for someone else, so I wasn't quite aware of this until yesterday. But I'm sure everything would be good, and I'll be able to give you a good insight on how global service load balancing may work. So this is just basically one opinionated approach, how this can be solved. I work for a cloud service provider in Berlin called SUS11. We're 170 people roughly. We have 5 different data centers distributed within Germany. So we ensure that we're GDPR compliant. We have a great deal of customers, as the Germans say, from the Dach-Region, so Germany, Switzerland, Austria, typically that host business critical applications at data centers within SUS11. And as the majority of you probably already know, if you're running on-prem clusters, if you're running stuff in your own data centers, there's definitely a few challenges that needs to be solved. And one of them, which I would like to tackle and talk about today, is server load balancing. Because within the majority of cloud service providers, you already have something in place which already very neatly takes care of this problem for you. So for instance, if you go to AWS, they, as far as I know, they announce their load balancers around about 150 different locations if you want to. Also, companies like Cloudflare have solutions in place which you can use. You cannot use these if you need to be GDPR compliant, if there's certain restrictions that you need to abide by, and this is basically where this idea came from to talk about global service load balancing. Okay, so let's get in. First, a bit about me. So I've been working at SUS11 since 2013. I like building Linux-related stuff on Raspberry Pis, home automation with Home Assistant, and all those sort of things, K3S. And if I'm not doing any of that and I need some movement, I like going out on my road bike or cyclocross and gravel cycling is one of my great interests. And there's lots of forests around Brandenburg which allow me to get out and about on my bike. We don't have hills, but we have wind. About the agenda. So first off, I would talk about load balancing basics or 101s. How does load balancing work? Why do we actually need load balancing? And what are we actually trying to solve? I'm sure most of this you are familiar with, but just to make sure we're all on the same page. Next, I will briefly talk about global load balancing commercial offerings. Not because I'm endorsed with any of these companies or they pay me for doing it. I just want to ensure that everyone believes that these solutions are also backed by other global players as well. It's not just something which has 1,000 stars on GitHub and this is the only people doing this. So there's like various companies already using these kind of technologies in different forms and variations. Some of them are very expensive, but we'll talk about this later on. The main open source solution I would like to present today is called K8 GB. So K8, obviously Kubernetes, GB Global Balancer. So it's basically a Kubernetes native solution. I'll give you a brief technical overview how this works and why you should maybe or maybe not use this. Pros and cons. So you've got a bit of insight into, what is good about this solution, and I also try to pinpoint something which is maybe not ideal or might be not ideal for your environment. It greatly depends on that. But of course, if you would like to discuss this, I'm up for discussions. And then towards the end, I would like to show you a quick live demo if this works, which I hope it will. I've set up a few things in our cloud to be able to show you this. Okay, so let's start off with load balancing basics. So load balancing in general, you're trying to solve a certain problem. You would like to distribute traffic across backends, applications in general, so that you can basically have your requests answered by multiple VMs, pods. So in my case, we're going to focus on pods. This is the general idea. And if you, of course, want to take this a step further, you could also be distributing traffic between multiple regions, or maybe even across different cloud providers if you want to do this. This could also be of interest. Why would you want to do this? Maybe it would save costs for you, or it can allow you to maybe use regions where one of your cloud providers doesn't even have a data center in. And if you look at certain, I mean, here in Europe, we're saturated with data centers, but there's a lot of areas in this world which aren't, which have different kind of challenges with their infrastructure and how to load balance this. So you would typically want to prevent server overload situations. So this is something which can happen fairly easy if for instance, your Apache is configured to accept 150 connections. If you have more than 150 connections, you're going to have some form of overload. This could be that some of your visitors see an unwanted error page, or if worse comes to the worst, it could even crash your entire server and it might not work correctly. So being able to distribute this workload is definitely helpful to prevent overload. It can do, it doesn't always, and to actually achieve this fully, you need to do a lot more than just switch on a load balancer and do this, because you need a lot of technical knowledge as well to be able to do this correctly. Normally, you should have some form of health checking of service. And no, I do not mean ICMP, ping your server. Ideally, you want a proper health check of your service. And a lot of web applications or frameworks for web applications, for instance, let's just take one of them, Spring Boot, already offer this out of the box. So you can build a health check which will actually see, does the connection to my database work? Does the connection to my key value store work? Is my application maybe even delivering a valid response? That is a proper health check. You should not be checking, is the server itself alive, or is only the socket alive? You should actually be seeing, am I getting a legit answer? This is something which I don't always see with clients of ours, which is one of the first things that we typically try and tackle when we look at load balancing. And is this service actually active? You definitely don't want to be sending something to a service which is delivering a 500, because the Apache is still working. A 500 is also coming from the Apache, or maybe coming from Apache. Often people want to solve SSL termination or offloading. So a lot of people use the load balancer in front of their applications for the TLS termination, because they normally believe that after the load balancer, all of the traffic afterwards is internal traffic, and this doesn't necessarily need to be encrypted. If this is right or wrong, this is debatable, of course, because if you're running on a public cloud, you could also say, okay, this is not my infrastructure. I should have mutual TLS into my application pod. So it's discussable, but this is something which is typically done. With service meshes and other things, you can also, there are also different solutions to this. And of course, you can also protect backend services, because generally your load balancer would, of course, need some form of public IP address, but your backend services might not. If they're running in the same data center, which they normally would do, unless you're using something like Cloudflare, maybe not, but even then there's something like, I think it's Argo Tunnel, I think they call it, which you could use. So that this would work without needing public IP addresses. But otherwise, you would typically use this to protect your backend services. So a hacker cannot directly attack your backend server. It can only attack your load balancer service, which is typically also going to be added to your A record in the DNS. So this can also be equipped with something like a web application firewall, or maybe denial of service prevention. So typically, companies like Cloudflare offer this out of the box if you need it. It all costs money, of course, but they have these sort of offerings. Okay, so how do we actually want to distribute traffic? Let's briefly go through there. A typical way would be round robin. Round robin means you have, for instance, for simplistic cases, let's say we have like 2 application pods, and we basically distribute the traffic between these 2 pods. It may be equally, it may not be equally. In some cases, it does not really matter. If you're doing this between multiple clusters, of course, there's additional things that you need to take care of, as in databases, client sessions, things like this as well. But this is typically the most simple form of load balancing. Then on top of that, you have something like weighted round robin, which can be used, where you can say, hey, my data center in Berlin should get more traffic than my data center in Munich, and I want to distribute, I don't know, 80-20 or something like this. This can also be done. This is also something which you see a lot of load balancers offer. You could say least connections, so the load balancer would count the number of connections that are hitting the load balancer at that point of time and say, hey, Berlin has 1,000 connections, Munich only has 500, so all of the connections are going to go to Berlin until Munich, until this is equal again. This is also something that a lot of people use as well. There's a cookie-based load balancing. Where would you need this? If you need some form of sessions persistency. So often, as I said, you have like some form of state within your application. I mean, in Kubernetes, we always talk about like stateless applications. It's a great thing. I've never seen anyone make money with a stateless application because as a business, you're going to need some form of state. It's either going to be your database or something else where you store information. If it's, for instance, an online shop, then you're going to have some form of cart or something which you want to check out, and you're going to need state. And maybe you want to direct the following request to the same cluster or to the same backend. So you're going to use some form of cookie, which at the end is an HTTP header, which you're going to do at the client, and then you're going to ensure that all of the following connections go to the same service. And then you can have failover, which also a lot of people use because for simplicity cases, it can be easier to do this. But if you just use a failover, which I'll also show in the demo, you're basically also losing a certain amount of, well, you could say resources, whatever you want to call it. You've got one data center where you basically do not send traffic to unless the other data center is not working. This is typically what you want to do with a failover scenario. And it's kind of good for a lot of use cases because it prevents you from maybe having to replicate your database consistently or to ensure that all the sessions are replicated between both clusters. But then again, it leaves you with this kind of setup where you're paying for something which you're not always using. So it can be annoying from a business perspective. And the last one, which is kind of very sophisticated routing, would be to do something like geographical IP. Normally, this is done with like databases, which with IPv6 can be difficult. They're not always up to date, and sometimes regional RNRs change the subnets, which may be assigned to, I don't know, to Slovenia, could now be Croatia or something. I mean, sometimes you have like providers that work between a border of smaller countries. So this does not always work as it maybe should do. But in general, you can also use these sort of things. A long time ago, people used to use DNS to do this. And then Google and Cloudflare came out with these awesome DNS services everyone was using. And then it didn't work as it used to. Because you weren't using a DNS server, which was local maybe to your region. You were using some global service. OK, so how does load balancing work in Kubernetes? So typically, you would have a user, a client on the left-hand side. This would apply to other systems or not Kubernetes as well. You would have some form of external load balancer, which then points to a service. So your external load balancer would have a public IP address. Your service does not necessarily need to have a public IP address. If you're using a cloud service load balancer, it would basically publish the service on a node port, on a host port, and then the load balancer would be the only one that would, if it was an HTTP application, open port 80 and 443. And then you would distribute the traffic to your pods. So this is in general super simple, and it's also a kind of security thing within a Kubernetes cluster. If you add a pod to a Kubernetes cluster, it's not published. So you cannot see it on the internet, of course, but that's what you want to do at the end. And to do this, you would typically use a service-type load balancer. So I took this from one of our clusters. This is an Nginx Ingress service. And as you can see, it has like an IP address. The selectors are missing here. I shortened that slightly, so it's not too much. And at the end, you see these are the node ports it's opening. So it's opening up a service port on 31.184 and at 32.718, which is then going to port 443 and 80. So this prevents a few things. This prevents you having to start your pod with a privileged port, which has slightly changed recently in Kubernetes, but this was normally, if you were running a pod on a privileged port, you would need to be root, which is generally a bad idea. So we would normally publish services on high ports. And high ports could be anything between 1024 and 65,635. And let's now switch to global server load balancing. So we've understood how typically load balancing works, which algorithms are available, and how load balancing works in Kubernetes. And let's first look at some commercial offerings of global server load balancing. So this is taken from Cloudflare. So global server load balancing, or GSLB, is a practice of distributing internet traffic amongst a large number of connected services dispersed around the world. So we're talking about Cloudflare. They always think things big, so you don't necessarily have to think this thing's this big. It could be just Berlin and Munich, as my example was previously. The benefits of global server load balancing include increased reliability and reductions in latency. So in general, we're trying to increase our reliability. If it always reduces latency, I would leave this undisturbed. It probably does for Cloudflare, but it won't do for everyone. Could be exactly the same latency. If we're talking about 2 DCs in Germany, for instance. What they're trying to say is, if you've got people from over the world coming to you, then it would be ideal if you can distribute a Brazilian client to a data center in Brazil, of course. So available on commercial offerings are typically, you can break this down into DNS load balancing, which I'm talking about today. IP Anycast, where you need specific Anycast networks to do this. This normally means that you're announcing the same IP address at multiple locations. This is what you can do with Anycast. It's fairly complex, and as I said, you need specific IP addresses. You cannot do this with a standard IP address. And it also brings additional trade-offs as well, because you need to ensure that if the service doesn't work at the location, it stops announcing this, which Anycast doesn't do by itself. You need some form of monitoring. You can use the border gateway protocol-based load balancing. So this is something which, if any network engineers in the room, you'll be familiar with this. This is the way the internet works. So routers talk to each other with BGP. And you can also use this to do load balancing too. So HA Proxy and a few other software stacks can use this. Content delivery networks, CDNs, typically do this. And global traffic managers, and also geographic load balancing, which I talked about earlier. So this would be the idea that you find out from which region someone's coming from, and that you ideally direct the traffic there. Yep. So yeah. I'm going to focus on DNS here because this is what the talk is built around. I just wanted to make sure that everyone is aware that other mechanisms are available. With Anycast, this could be done fairly quickly, but as I said, you're going to need certain mechanisms to actually do this, because you need to de-announce a route. Otherwise, this is not going to work. With BGP, similar. Global traffic managers greatly depends on the service you're using. These are normal commercial offerings normally. I don't know of any open source offerings which actually would do this. So, and with geographic load balancing, you typically don't need to change all that much in the majority of time. You would just probably redistribute someone to a data center which is further away from him if that data center went down. And then, of course, you would have a higher latency would be the impact. DNS, I will talk about this in a minute, a bit in depth. It definitely has a few issues, of course, with switching over. So that's definitely a valid argument that you have. So let's quickly go through the commercial offerings that I came across. These are not, these are not all of them, of course. There are a lot more available. I just wanted to show you a few. So there's like AWS has a global accelerator, which, as far as I understand, is based on Anycast. Cloudflare load balancing is also based on DNS. So they also used a global server DNS load balancing approach. F5, which the company now also behind Nginx and a lot of other appliances, they've run something called Big IP, which many years ago we also used to run one at sys11 with global load balancing. It basically also uses DNS to do this. And Akamai, I believe, also use DNS. Akamai are one of the largest CDNs in the world, in case you don't know, in case you're not familiar with them. And they also use a similar system. As I said, I just wanted to ensure that you're familiar. This technology is also used by other vendors and not just the service which I'm trying to, which I want to talk about today. So cloud native, K8s, global load balancer, K8GB. Where does this come from and what does this actually do? So number one, it's a CNCF sandbox project. So as you've probably seen, if you've ever seen the CNCF landscape, it's huge. There's so many different software on there, and it's difficult to keep track. Typically, if they get past some form of incubator status, they've definitely got a great deal of hope of staying there. But this is something which is never 100% sure. But as this technology can be used by various software, I don't think this is going to create a great issue. It's Kubernetes native, so it only runs in Kubernetes. It's basically a containerized approach, and it also uses custom resource definitions, which I'll go into in a minute. It was built by APSA Group, I think they're called. As far as I know, I did a quick research on them. They do online banking and other banking applications in South Africa. And in their brief outline that they stated it was also because of financial aspect was one role, but also because they did not have enough cloud providers they could actually work with in South Africa. So that's why they actually decided to build this piece of software. It uses existing open source components, which is something that I really like. Maybe some of you are familiar with Core DNS, which is the main DNS software within Kubernetes. So in Kubernetes, basically everything relies on DNS because pod IPs can change at any given time. So in general, if you would have a WordPress and its database, you would not add the pod IP of the database to your WordPress. You would add the name of the service. And that service would then be resolved by Core DNS. And another component it uses is external DNS. In case you're not familiar with external DNS, it's a part which also runs within your Kubernetes cluster. It watches certain resources, which are typically ingresses, gateway API, or services. And if one of these services has a public IP address, for instance, the ingress controller would typically have a load balancer service, which I showed you earlier, and it would add this to your DNS. How does it do this? So it needs, first, it needs a supported DNS service, but the list of DNS providers is quite long by now, and you can also add plugins to add your own DNS server. Your DNS server, of course, is going to need an API endpoint that you can authorize against, so it's got some form of token. For instance, it's Route 53 or Cloudflare, they all have API-compatible DNS services, and then it will basically update your DNS record for you. So if your IP changes, it will, in a few minutes, it will reflect the new status of your IP address. So that's the idea behind custom DNS. And global server load balancing, in this case, K8GB, uses so-called subdomain delegation. In case you're not familiar with this, I will show you a picture in a minute where you can see a bit more about the topology of this. But basically, what you do is you may have a main domain, say example.com, and it's hosted by Route 53. And then you would take part of your domain, let's say cloud.example.com, and you would delegate this part to another DNS server. And all of the requests of cloud.example.com and any underlying subdomains would then be answered by another DNS server, so not the main one. This is typically how subdomain delegation works. So you need no specific hardware to do this. So it will run on any of your clusters. You could even run it on your home lab if you wanted to. It can basically run anywhere you want, as long as, of course, you can run Kubernetes. You typically have no single point of failure because we're using the DNS infrastructure. And DNS infrastructure, if you're using one of the well-known providers, it's versatile, it's stable, it's been around for a long, long time. It was one of the first services next to HTTP that the internet's built on, because without DNS, we'd all be typing IP addresses into the browser, which would be awful. You don't need any cloud load balancer, so you can potentially save some costs here, because cloud load balancers can be expensive, depending on which cloud provider you're using. So AWS, as far as I know, charge you differently depending on what kind of cloud load balancer you want. So you can have like application-based, which go up to layer 7. You can have TCP-based, which only go up to layer 4, as far as I know. And I think there's some other ones as well. But so the cost can greatly depend. And also, looking at AWS, they also charge you different depending on what region you're in. Some more popular regions are more expensive. So the cost could be fairly high. A quick look at the time. It relies on stable DNS infrastructure. So it doesn't always, of course, mean that your DNS infrastructure has to be stable, but typically if you use one of the providers I outlined, it should be. And you have different strategy options, which we talked about earlier, so I'm not going to go into this any deeper, but these are the supported strategies you can use with K8GB. And these are all supported. If you want to use GeoIP, that's the only specific one. I haven't tested this. I only tested round robin and failover, which I will demonstrate here. If you want to use GeoIP, you're going to need something like a MaxMind database to be able to, as I said, you need to find out with a local database to which country these IPs belong. And it should be up to date as well, otherwise this could change. And as I said, I'm not 100% sure how this is going to work for IPv6, how good this actually works. I've not tested this. I'm not sure if anyone knows about this, but it's not something I've really looked into, and there's a lot of IPv6 nets. So let's go into a technical overview. Oh, this is a bit difficult to read, I think. So the idea behind this, if you look at the at number 1, is that we have a zone delegation. So in our test, we're using cloud.example.com, which I just spoke about, and we're doing a zone delegation, and we want to delegate the zone cloud.example.com. We have 2 Kubernetes clusters, so one running in the US on the left-hand side, and one running in the EU on the right-hand side. And if a request hits cloud.example.com on AWS Route 53, we're going to send that request to the core DNS running in the local cluster. And the controller, the K8GB controller at the top, is going to create entries in Route 53. So to be able to do this, that's why I say you definitely need a DNS provider with an API. The controller needs access to the Route 53 API. So it's going to need some form of token, which is hopefully limited to your DNS domain that you're running and not to your entire AWS infrastructure, please, if you're running on AWS. And this would give you the option to add records. So it would add a record for the subdomain delegation, and it can also add additional text records to ensure that it knows which instance of external DNS added this entry. In case you ever want to delete this, it can automatically delete this. It can recognize this. So at this moment, if we look at number 3, the KGB does not know about the other KGB. So if you would hit it, it would only give you the records of the cluster in the US. Once the EU cluster is also online, it's going to basically do the same thing. It's going to add its core DNS for subdomain delegation. So we'll then have 2 entries maybe, depending on how many core DNSs we're running. And we could answer requests from the US and the EU. The controller is then going to iterate through all the records, which are on Route 53, and it will find the other cluster. So the EU cluster will find the US and vice versa. And then when we return the A record, we will then, in my case, in my demonstration, we won't get 2 IP addresses back, we'll get 4 IP addresses back if we have 4 worker nodes, which we're distributing our traffic in between. And the core DNS in both clusters will then update their entries for both clusters. So the EU will update its core DNS with the US entries and vice versa. From then on, the records are then shared. So if you see in the bottom, if the request then hits the service, you then receive these 4 IP addresses as the DNS response, which will then, depending on your strategy, allow you either to fail over or to round robin between the EU and the US. Sorry, this was a bit small. I hope you were able to recognize everything. If anyone has any questions so far to this, then I can answer them straight away while we've got this on the screen. Otherwise, I will continue, and hopefully the rest of how this works will be clear when we look at the demonstration. So what are the pros and cons about building this kind of setup? So one of the pros, easy setup. Most engineers are familiar with DNS, right? I hope we all agree on that one. Most of the people that work in your company have probably heard something about DNS, are roughly familiar how this works. So there's no new technology, basically. Multiple algorithms are available to do load balancing with. I explained this. So you have like 4 or 5 different algorithms you can use. It's easy scalable to multiple clusters because next to our EU and US cluster, we could have an Asian cluster, or we could have another EU cluster if you wanted to, and we could just add these records to the DNS as well. One of the trade-offs that I see is running a DNS server in my Kubernetes cluster can cause certain attacks. So an amplification attack, which is a typical DNS attack, could be one of them, but there's probably multiple others which could also affect you. So you're basically exposing on port 53 UDP and TCP a new service core DNS, which normally in a Kubernetes cluster you would not do. Just to be sure that we're on the same page, you're not actually exposing the core DNS from the Kubernetes cluster itself, but you're actually installing a new core DNS. So you're not giving any internal information about your core DNS. It only about your Kubernetes cluster. Sorry, it's only answering the request for those delegated domains, but it can still cause potential problems. And there's one thing which is difficult to rely on. I'll quickly show you this in the demo as well. Is DNS TTL, because this is something which is done on client side. The majority of clients and also DNS resolvers within ISPs now reflect the actual TTL because most of these companies are aware of this situation, that within cloud environments, IP addresses can change, people can get redirected to different data centers and other things. So most people now respect the TTL. But you don't know if they're going to do this. You don't know if the client you're using just decides, okay, I'm going to cache this IP address for the next 2 hours or something stupid instead of the 60 seconds that you stated in the TTL. People could theoretically override this, so you're relying on something that you can't change. This is the only other trade-off that I could actually think about. Okay, so let's quickly go through the demo setup, what I actually set up. So our managed Kubernetes is called Metacube. So I set up 2 Kubernetes clusters or Metacube clusters in 2 different DCs. So we have one in Hamburg and one in Düsseldorf. This is what I'm going to show in the demo in a minute. There is a KGB installation, with Helm. So I installed the Helm chart and configured it. I'll show you this too. I have a failover domain and a round robin subdomain. I took easy domain so you can actually see this happening. Of course, you can point any other CNAME to that main to that delegated domain as well, which I also did. I chose the DNS hosting by Cloudflare. It was just simple, and I already had a Cloudflare account, so I just used this. But as I said, you can use any DNS provider which is supported by external DNS. That shouldn't be an issue. And I deployed an Nginx ingress controller as a daemon set. Daemon set means it's running on every single node in the Kubernetes cluster. I only use very small Kubernetes clusters, so each Kubernetes cluster has 2 compute nodes or worker nodes, which the Nginx ingress controller is running on both of them. As I said, I'm not using any form of cloud load balancer in the setup. Everything that I'm doing is done via host ports and the Ingress controller. And last but not least, I also installed a test application so we can see that something is happening. We have something that responds at the back end with an Ingress rule in each cluster. And oh yeah, and I also have a CNAME. We don't need to use this. I just wanted to point out that you don't just have to use the subdomain you're delegating, because you probably don't want to just publish your application under, I don't know, app.cloud.example.com. You probably want some form of shorter domain as well. So you can also point CNAMEs to the delegated domains as well. That's also possible. Okay, let's go into the demo then. I'll quickly get a chair and sit down. It's easier to type then. And then it would be nice if someone could say if they can see everything or if it's too small. And maybe because I'm getting older, my screen is too small, maybe need my glasses. Is this large enough for you guys to see? No? Oh, okay. Okay. What about this? Is it better? Okay, let's do the same here then. Okay. Okay, so as I said, we have two Kubernetes clusters. As you can see at the top, one is in Düsseldorf and the other is in Hamburg. And we have both have Helm charts for KHGB, for Nginx Ingress, and the GSLB is basically a small pod called pod info, which I'm using to basically show you an application. And exactly, I'll go away. I'll get rid of this. Thank you. And in the other cluster, we have exactly the same. So these are basically the software which I've installed. So if you have a quick look, we have like different namespaces, and the namespaces we're going to look at GSLB, KHGB, and Nginx Ingress. So number one, let's have a look at the Ingress. I'm just going to use one cluster to do this because I'm slightly running out of time. So as I said, we have the daemon set, and the daemon set is running across 2 nodes. So it's like a 2-node cluster. And as you can see here, you have 2 nodes. They both have public IP addresses, and the same here for the other cluster, 2 nodes, 2 IP addresses, and it also has the Nginx Ingress running. Also a daemon set and a default backend. So if we curl any of these pods, any of these compute nodes, we should receive a default backend 404. If anyone wants to know why, because we're not sending a host header in Ingress, you need to send a host header. Okay, so next up would be, let's have a look at the configuration. So the Ingress controller, I'm going to jump this part, and if anyone's interested, it's basically just a simple Nginx controller. The only, let's quickly have a look at it, I suppose. One thing that's maybe worth showing is it has a small rule here to be able to also publish port 53 UDP on. So just so you're aware of this, the core DNS is also being published, as I said earlier. And if we have a look at the other namespace, which is GSLB, you will see, sorry, it's not, it's K8. That's the first one I wanted to show. Yeah, there it is. You will see we have 3 pods running. So there's a core DNS running, which was deployed by the Helm chart, the K8GB, and the external DNS. And the K8GB also brings its own CRD. So if we look at the CRDs, you will see it brings one single CRD with it called GSLBS. And if we have a look at this, get GSLBS, you will see it's namespaced. And in the namespace GSLB, where my application is, you see we have 2 different strategies, a failover and a round robin strategy with 2 different domains too. We have the same in both clusters. So this is identical. And what does this look like? This looks like, so a quick look. Let's take the Düsseldorf implementation. This is basically all it is. It has a domain at the top, a subdomain which we're delegating. It has an edge DNS zone which we're using, and a Cloudflare zone ID. to run off, so it knows which zone ID. This is specific to the DNS provider you're using. This could be slightly different with AWS. So you basically configure which DNS provider you're using. And yeah, that's basically it. In the ingress rule itself, this is also important. So the ingress rule basically sets up the ingress controller to accept traffic for a certain domain. So if we look at this at the top, probably the most of you are familiar with this, is a typical ingress rule, and I'm using the domain failover.cloudflare.cloud.aycde. And one additional thing I'm doing here, which is a bit, you can do this in Ingress. You can basically add additional HTTP rules, and then you can add additional names to an Ingress rule. And I'm using the service pod info. Underneath is the actual configuration that you need for the GSLB. As you can see, kind is the custom resource definition, so GSLB. And in this case, I called it failover because it is a failover. And in the strategy here, you see what type it is. Here I added this comment basically, which if you're using non-enterprise Cloudflare, which I'm using, you're limited to 60 seconds as a TTL. Oops, 60 seconds for a TTL. So this is then limited to your failover time, of course. And I have two data centers, which I abbreviated with ham and dus. My primary tag for the failover is ham, because in a failover scenario, you need to say who is the primary. So have I forgot something? No, I don't think so. So the only thing that I didn't show is the application. The application is a simple single pod. So let's quickly have a look at this in the browser, what this would look like. I didn't do SSL or anything, so it's like a simple application. Here is my application in Hamburg. So basically, this is answering, and let's maybe use curl for this for simplicity reasons, because it's basically easier to do this with curl. And let's just hit our failover domain. So you can see here, all requests are being answered by Hamburg. And yeah, let's go to Hamburg and basically scale down Hamburg and simulate something broke. So to do this, we could basically use kubectl. We can go to our namespace. We can scale. We can say replicas is now 0 for the deployment, pod info. Pod info scaled, and now it's 0. So at the moment, the service is temporarily unavailable. And the service is basically down and not reachable. And hopefully, if everything works, the other data center should take over. Let's see and check what our DNS is saying. And what we could do is we could use dig and go to the failover domain. Let's have a look. Where is it? There's a round robin failover. And the failover domain already has 2 IP addresses. And the 2 IP addresses should reflect Düsseldorf. As you can see, the 2 IP addresses that came back are these 2. And if we go back up to the entry for Hamburg, you can see that this is not the IP address of Hamburg. So let's have a look. In the other data center, we've got 117 and 39. And if we do our dig on failover, you can see this reflects 117 and 39. And answers are coming back from curl. It stopped now because I only did 1,000 requests, but we can see the answers are coming back. So we had a brief downtime while we were failovering until the IP addresses were changed. If you scale this back up again, I believe, if I remember correctly, that it will not automatically change back. Because why should it? I mean, it doesn't really make sense, right? Let's see if it does or not. I don't think it does. I think it will change on this DC because we still said our primary DC is Hamburg, but switching back would just basically cause additional interruption. I don't think it actually does this. But let's wait a minute and see, or we can look towards the end and check what actually happens. But I believe, if I remember rightly during my test, it definitely stayed on Düsseldorf. So this would be our failover scenario. So our data center in Düsseldorf has failed. In Hamburg, sorry, has failed. We switched all traffic to Düsseldorf. We had a brief interruption, but that was very short. And basically, our service is up and running again and no issues whatsoever. So next scenario would be, let's have a look at the round robin scenario. So we want to distribute traffic between these two. As I said earlier, there's additional precautions need to be taken here, especially if you're running databases, sessions, and other things. It's not as simple as I'm outlining here, but it can definitely be done. Oh, sorry, I wanted to show the ingress rule for this. Round robin. So as you can see, the ingress at the top is basically the same. I'm just going to skip this because we've already seen this. The difference here is the strategy. So the strategy here is round robin. That's the only thing that changes. And we do not have a primary data center anymore because we don't need one. We're distributing traffic between both data centers, right? And let's have a quick look with dig. So if we check round robin, you can see that if you remember, the two previous IP addresses are included here because we're using the same clusters, of course. But now it's not delivering 2 A records in return or 2 IP addresses. It's giving me 4 IP addresses. So this reflects all 4 worker nodes. And in a browser, this does not always work super reliable, but with curl, it does. Because browsers have basically their own mechanisms of staying on a service. Here you can see it's fairly quickly, but you can see it's switching between Düsseldorf and Hamburg. And if we do the same again and scale one of our data centers, just take the other one this time maybe, and scale. Oops. And scale this deployment to 0. So I'm scaling the deployment in Düsseldorf to 0 now. So this should get no requests in a minute. And you can see it's switching between temporary unavailable and Hamburg. And okay, we've time out. We've done 1,000 requests now. And after a while, you will see that all of the requests will only hit the data center in Hamburg. As I said, it takes a few seconds to reflect the new configuration. Let's maybe have a look at dig quickly as well. Dig is only answering 2 records. Of course, we can have caching in between because I'm not directly asking Cloudflare. Of course, I'm asking some form of resolver in between, and that also has caching, so it needs to receive the new information which is changed. Whereas when I'm using this request, you can already see it only reflects 2 IP addresses. So this was done without any intervention by myself. No on-call duty had to get up. We did not have to do anything else to do this. And we didn't have to pay a lot of money to some huge enterprise to do this either. We could do this with a application which I can install by myself within Kubernetes. And once I scale back up, of course, it will then reflect the new configuration again. And this would work the same if you were adding additional clusters as well. This will take a few seconds, and then you will see it will add the additional IP addresses back again, and then we will be able to load balance. It always seems to take ages when you're sitting there watching it. When you're sitting at home, it seems to go a lot quicker. And you can already see this is already reflecting now the 2 clusters. Strange. Maybe this is also my local cache as well then, because you can already see this is already working here. But so this is, as I said, the only downside I can really see on this, that you're basically relying on a certain amount of cache. As I said, with Enterprise Cloudflare, you could probably eliminate this down to 30 seconds. You're not going to be able to go any further than 30 seconds because most of the clients will not allow you to do this. That's strange, it's taking so long. Okay, then let's go back to the last slide. And that's the end of the demo and what I really wanted to show you. And what could next potential steps be to improve this setup? I've put a few links together for you guys to maybe have a look at of software which I find could be helpful in increasing the multi-cluster experience within your Kubernetes cluster. So one of them, which I've already used, is Liku.io, which basically builds a seamless Kubernetes multi-cluster topology. It uses WireGuard to do this, so you can use this on-prem as well. It basically builds a WireGuard mesh to allow you to have like local visibility. Cilium, maybe a lot of people are familiar with this already. It's a CNI for Kubernetes, which also allows you to do a multi-cluster. It has one downside though, it already needs local visibility. So you either need some form of VPN or if your cloud provider has this, maybe a VXLAN or something like this to have local visibility between the two Kubernetes clusters. And if you want to deploy to multiple Kubernetes clusters at once, then maybe you want to look at something like Admiral to do this. That will allow you to deploy to multiple clusters at once. Because if you were doing something which I outlined, you probably want to have your pods, of course, in two clusters, and you normally don't want to separately deploy to two clusters. Okay, so that would lead me to the end of my talk. I think I'm just a bit over time, but only by a few minutes. Does anyone have any questions to Kubernetes or to global server load balancing? Yep. So the only limitation would probably be the number of IP addresses you can add to the DNS. So that would greatly depend on your DNS provider. So I probably wouldn't recommend on probably giving back 100 IP addresses or something. That would probably being a bit overboard. But we've tested it like with about 20 and it worked without a problem. So if you're running two Kubernetes clusters with 10 nodes in each, then that should be absolutely okay. That's the size I've tested with. I'm sure you can do more if you really wanted to. And there's probably, as I said, some form of limit on how many records you can add to certain DNS providers. But I would assume that most of them would allow you to add quite many or a lot of DNS records. Are there any other questions? Okay, then. Oh. The CRD for KGB? Is this what? Sorry, I didn't. Yeah. It's a stable API. Yeah. Yeah, it's been around for quite a while. I think they started the project in 2019, I think, if I remember correctly. And as I said, I hope it should be an incubator project very shortly. So they told me anyway. Okay, then thank you very much for your time. And I hope you enjoy the rest of the conference. And if you would like to talk about anything related either to Sys11 or to load balancing, you can find me over there at the Sys11 booth. Thank you very much.